Welcome to the Deep Dive. We're the show that unpacks vital insights from, well, often a stack of sources, giving you that shortcut to being truly well-informed. Today, we're diving into something really fundamental. It's often unseen, actually, but it impacts our safety, the stability of everything around us. Think about real-world stuff, like how a concrete column might just fracture after an earthquake. That's a critical point right at the top of our source today, a fantastic textbook on the mechanics of materials. It really makes you wonder, doesn't it? How do engineers stop that? How do they, predict what a bridge or a building or even just a simple car part can actually handle before it breaks? So that's our mission for this deep dive, understanding the mechanical properties of materials. We're going to explore these really ingenious experimental methods engineers use, methods to discover the inherent strength, you could say, of these materials. And it reveals some surprising insights into why they behave the way they do under stress, and crucially, how they eventually fail. All right, let's pull back the curtain on this a bit. To understand why that concrete column failed, we first need to get a handle on how engineers figure out a material's basic strength. And the bedrock for that, the absolute foundation, is a key assessment, the tension and compression test.
Yeah, and what's really fascinating here is that the strength of any material is, well, it's inherent. It's built right into its structure, its very makeup. We can only truly grasp it by, putting it through its paces, testing it.
Right.
And that's exactly why this tension and compression test is so vital. It reveals that fundamental relationship between stress, average normal stress, technically, which is like the internal force per unit area,
Okay.
and average normal strain, which is basically how much it stretches or compresses relative to its original size. And knowing this is just critical for everything from metals to ceramics, polymers, composites, you name it.
So how does it actually work? What's the setup look like?
Okay, picture a standardized piece, a specimen. Often it's a steel rod, maybe 13 millimeters in diameter, and it has what's called a gauge length, usually about 51 millimeters. That's the specific section where we take the measurements.
Got it.
This specimen gets mounted in a special machine, and then it's stretched very slowly at a constant rate until it breaks, it fails. While the machine is applying that load, really precise devices, things like extensometers or electrical resistance strain gauges, are constantly measuring the elongation.
The stretching.
Exactly, the direct strain between two little punch marks on the specimen. It's quite meticulous, yeah, but the data you get is incredibly rich.
And that raw data, the load and the stretching, that's where the real insight comes from, isn't it? It all comes together into this single powerful visual, the stress-strain diagram. You called it like a material's unique fingerprint. Its life story under stress.
That's a perfect way to put it, because this diagram, this fingerprint, it's so fundamental. It's the map engineers use, really, to navigate what a material can do. And importantly, it applies regardless of the specimen size. Now, we usually talk about a conventional stress-strain diagram. That one uses the original cross-sectional area and the original gauge length. There's also a true diagram that accounts for the instantaneous changes as it stretches and mechs down. But for most engineering design, especially in what we call the elastic range, that's where you need things to return to their original shape. The conventional diagram is perfectly accurate. It works.
It simplifies things, but still gives the right answers for safety.
Precisely. It avoids unnecessary complexity where it isn't needed.
So this diagram, it isn't just a simple line. You said it's like a story with chapters. For something like steel, a ductile material, you mentioned 4 distinct regions, each telling us something different.
Exactly. Each region reveals a different aspect of its behavior. So the first big question is, what happens in each of these? First up, we have elastic behavior. This is the initial part, usually a straight line on the graph.
Right.
And the key thing here is, if you take the load off anywhere in this region, the material snaps right back. It completely recovers its original shape. No permanent damage.
Okay, that's crucial.
Absolutely. And this is where Hooke's law applies. It basically states that stress is directly proportional to strain. Simple relationship. The slope of this straight line, that's the modulus of elasticity, or Young's modulus, named after Thomas Young, published on it way back in 1807.
Wow.
Yeah. And this value, we call it E, it tells you how stiff a material is, how much it resists stretching.
So high E means very stiff.
Exactly. Steel, for instance, incredibly stiff. Its E is around 200 gigapascals GPa. It takes immense force to stretch it even a tiny bit. Compare that to, say, spongy rubber. Its E is tiny, maybe 0.69 megapascals MPa. It deforms very easily. So E is this direct measure of resistance to deformation. It's fundamental.
So Okay, like bending a paper clip just a tiny bit and it springs back. That's elastic. That makes perfect sense.
Perfect analogy. That spring back is the elastic recovery.
But if you bend it too far,
Right. If you go beyond that elastic limit, even a small increase in stress starts causing permanent deformation. This is called yielding. The stress level where this yielding begins is the yield stress, or sometimes called the yield point.
and it stays bent.
It stays bent. Now, for some materials, like low-carbon steels, you might actually see an upper and a lower yield point. It's a bit of a quirk.
Interesting.
Yeah, the stress might drop slightly just as it starts to yield significantly, but once yielding really gets going, the material keeps stretching without needing much more load. It behaves almost like elastic, perfectly plastic is the term.
Meaning it's past elasticity but stretching easily now.
Correct. It's permanently deforming. Then things change again. We move into strain hardening.
Strain hardening. So it gets tougher.
Sort of, yeah. As you keep pulling on it, any further increase in load actually makes the material stronger. It resists further stretching more effectively. So the curve on the diagram starts to rise again, though maybe not as steeply as before. It continues rising until it hits a peak. That peak stress is called the ultimate stress. That's the maximum stress the material can handle on the conventional diagram.
Okay, the absolute limit it can take, load-wise. So after pushing it that hard, through strain hardening, what happens next?
Yep.
The final stage before it actually breaks.
Right, then comes the dramatic part, really, the necking region. Just after it hits that ultimate stress, something visible starts happening. The cross-sectional area of the specimen begins to decrease, but not uniformly. It starts shrinking down in one localized spot.
It forms a neck.
Precisely. And all the strain starts concentrating right there in that neck. It stretches rapidly in that small zone until finally the material breaks. The stress value, right at the point of breaking, is the fracture stress. And for ductile materials like steel, the break itself often has this characteristic shape, a cup cone fracture surface.
Ah, a visual clue about how it failed.
Exactly. It tells you it failed in a ductile manner.
Okay, this brings us right to that key distinction you mentioned. Ductile versus brittle materials. What's the practical difference? Why does it matter so much for, us relying on these things?
It matters immensely. Ductile materials like the mild steel we've been talking about are often preferred in engineering because they can undergo large strains before they actually fracture.
They stretch a lot first.
A whole lot. And this is critical for safety. Why? Because they give you warning. They visibly deform, bend, stretch, bulge before they fail completely. Plus, they can absorb a significant amount of energy like shock or impact because of all that deformation.
How do you measure that ductility?
We quantify it, usually with percent elongation, how much longer it got compared to its original length. For mild steel, that could be, say, 38%. Or we use percent reduction in area, how much thinner the cross-section got at the fracture point. For mild steel, maybe around 60%. Those are big numbers.
Yeah, that's a lot of stretching and shrinking. It definitely signals trouble before a complete break.
Absolutely. Now, connecting this to the bigger picture, not all materials behave so neatly. Some, like aluminum, don't show that distinct yield point like steel does.
So how do engineers define its yield strength then?
They use what's called an offset method. They draw a line parallel to the initial elastic slope, but offset by a certain small strain, typically 0.2%. Where that line intersects the stress-strain curve, that's defined as the yield strength. It's a practical, consistent way to do it.
Clever. A workaround.
Exactly. And then you have materials like natural rubber, a polymer. It doesn't even really have a proportional limit, that initial straight line. It just shows nonlinear elastic behavior right from the start. Designing with that is a whole different challenge.
Okay, so that's ductile. What about the other side? Brittle materials.
Right, brittle materials, think gray cast iron or concrete or even glass. They exhibit very little or sometimes no yielding at all before they fracture.
They just snap.
Pretty much. They absorb very little energy compared to ductile materials, and the failure can be sudden, catastrophic with almost no warning. Take gray cast iron. Its tensile strength, its ability to resist pulling is actually quite low. It breaks easily in tension, but it's much, much stronger in compression when you squeeze it.
Ah, so that's why concrete structures almost always have steel reinforcing bars, rebar inside them.
Precisely. You've got it. Concrete is fantastic in compression, very strong, but it's terrible in tension, very weak.
So the steel handles the pulling forces.
Exactly. Concrete's compressive strength might be, say, 12 or 13 times greater than its tensile strength. So you embed steel bars, which are ductile and strong in tension, right where you expect those tensile stresses to occur. It's a composite material, really, leveraging the best of both.
Makes sense.
And it's also really important to remember that the line between ductile and brittle isn't always sharp. Many materials can actually exhibit both types of behavior.
Oh, how does that happen?
It depends on various factors, like chemical composition. Changing the carbon content in steel, for example, can make it harder but also more brittle.
Okay.
Or temperature. Temperature has a huge effect. Many materials that are ductile at room temperature become brittle at low temperatures. Think of plastics getting shatter-prone when frozen. Methacrylate, plexiglass is a classic example, much harder and more brittle when it's cold.
That's a critical design consideration then, depending on where something will be used.
Absolutely vital. You have to consider the operating environment.
Okay, so we understand how things stretch, yield, and break.
Mhm.
What else do engineers glean from these tests? What other properties are important for designing real-world things? You mentioned strain hardening again.
Right, let's revisit strain hardening. Remember, if you load a ductile material past its yield point into the plastic region, and then you release the load.
It doesn't go back to the start. There's some permanent bend or stretch.
Exactly, there's a permanent set. But here's the interesting part. If you immediately reload it, starting from that permanently deformed state,
Yeah.
it will now follow a new elastic path parallel to the original one up to a higher stress level before it starts yielding again. Its yield point has increased.
So bending it actually made it stronger in a
Yeah,
way,
yeah.
harder to bend again.
Precisely. You've increased its yield strength through plastic deformation. This is sometimes called cold working in manufacturing.
Like bending a wire back and forth, it gets harder each time.
That's the phenomenon. The trade-off, though, is that you've used up some of its capacity for further plastic deformation. It becomes less ductile. Stronger, but more brittle.
Okay. A trade-off.
Yeah.
Strength versus ductility.
Always a trade-off in material science, it seems. Now, another key aspect is energy. When you deform a material, you're doing work on it, and that energy gets stored internally.
Stored energy.
Yes, strain energy. And we can quantify how much energy a material can store per unit volume. That's called strain energy density. Graphically, it's simply the area under the stress-strain curve.
The area under the curve represents energy.
That's right. And there are two specific measures of this energy storage that are really important. First is a modulus of resilience. That's the strain energy density just up to the proportional limit, the end of that initial straight line elastic region.
Okay, so the energy it can absorb and still spring back perfectly.
Exactly. It represents the maximum energy the material can absorb without suffering any permanent damage. Think about why that's important.
Things that need to take a hit and recover, like car bumpers or springs.
Perfect examples. Bumpers, shock absorbers, springs. They need high resilience to do their job without getting permanently dented or deformed after an impact or load cycle. Then there's the modulus of toughness. This is the total area under the entire stress-strain diagram, right up to the point of fracture.
So resilience is elastic energy, toughness is total energy absorption.
You got it. Toughness represents the total energy a material can absorb before it breaks. This is critical for components that might face accidental overloads or impacts that go way beyond the elastic limit.
Like things that need to fail gracefully or at least absorb a lot of energy before they go.
Exactly. Think crane cables, structural components in earthquake zones. You want high toughness so they can absorb a massive amount of energy before fracturing. And interestingly, engineers can tweak both resilience and toughness in steel just by adjusting the carbon content.
That's incredible control. So we're looking at how much give a material has, both elastically and right up to failure. Now, you mentioned something else happens when you stretch things. They get thinner.
Ah, yes. That's Poisson's ratio. It's named after Simeon Poisson. It's a simple ratio, actually.
Okay.
It describes the relationship between the strain happening sideways, lateral strain, and the strain happening lengthwise, longitudinal strain, when you stretch or compress something.
So stretch it long ways, it shrinks sideways.
Right. Poisson's ratio is the ratio of that lateral shrinking strain to the longitudinal stretching strain. It's a dimensionless number, no units. For most solid materials, metals and such, it's typically somewhere between 0.25 and about 0.35. Cork has a Poisson's ratio near 0, interestingly.
And rubber.
Rubber is closer to the theoretical maximum, which is 0.5. That's why when you squeeze a rubber block, the sides bulge out quite noticeably. It tries to maintain its volume.
That makes sense. I've seen that.
It's a fundamental property relating deformations in different directions.
Okay, we've mostly talked about pulling, tension, and pushing compression. What about twisting or sliding forces? Shear.
Good point. Materials absolutely experience shear stress too. Think about bolts holding plates together or an axle twisting. And just like for normal stress, we can create a shear stress strain diagram by testing a material, usually by twisting a tube or cylinder. In the elastic region, there's a similar relationship. Shear stress is proportional to shear strain.
Another straight line.
Yep. And the constant of proportionality here, the slope of that line, is called the shear modulus of elasticity, or sometimes the modulus of rigidity. We usually denote it with G.
So E for stretching, G for shearing.
Exactly. And these properties aren't totally independent. There's actually a mathematical equation that connects E, G, and Poisson's ratio. So if you know two, you can calculate the third for many materials.
Fascinating how interconnected it all is. Okay, so far this has been about loads applied steadily, or at least relatively slowly. But you hinted earlier, what about loads that stick around for a very long time, or loads that are applied over and over and over again? This feels like where things might get sneakier. The silent destroyers, maybe. Creep and fatigue.
That's a good way to put it. Yes, many real-world components face conditions that lead to these kinds of failures. They're time-dependent or cycle-dependent. Let's take creep first. Creep is basically slow, permanent deformation that happens over time under a sustained load. It's often associated with high-temperature sink components inside jet engines or power plants. Metals can slowly deform under load when they're hot.
But does it happen in normal temperatures, too?
It absolutely can, especially in materials like polymers, plastics, and rubbers, and also concrete. Think of a heavy shelf supported by plastic brackets slowly sagging over years,
Yeah.
or a wooden beam in an old house gradually bending under the roof load, or even just a rubber band held stretched for days it won't fully spring back. That's creep.
So it's a slow, gradual stretching or deformation under constant stress.
Exactly. It's time dependent, and engineers absolutely have to design for it in long-term structures or high-temp applications. They use something called creep strength. That's basically the highest initial stress a material can handle for a specific amount of time at a specific temperature without the creep strain exceeding some acceptable limit, maybe like 0.1% strain per year for bolts in a turbine.
Got it. Designing for the long haul. What are the other one? Fatigue.
Hey, fatigue. This is a huge one, probably the most common cause of failure for metal components subjected to repeated loading.
Like engine parts, bridges.
Exactly. Engine crankshafts, connecting rods, aircraft wings, bridge supports, rotating shafts, anything that sees stress levels go up and down again and again. Fatigue happens when a material is subjected to repeated cycles of stress or strain. Here's the really insidious part.
Yeah.
The failure can happen even if the maximum stress in each cycle is well below the material's yield strength. It could be operating entirely within its safe elastic zone, according to a static test.
Wait, how? If it's not yielding, how does it fail?
It starts with tiny imperfections, microscopic flaws, inclusions, or even just surface scratches. Under repeated loading, these tiny flaws act as stress concentrators. Tiny cracks initiate at these points and then grow very slowly with each stress cycle, little by little, cycle after cycle,
Until what?
until the crack gets large enough that the remaining cross-section can't handle the load anymore, and then suddenly it fractures, often catastrophically, and the fracture surface often looks brittle, even if the material itself is normally ductile. There's very little warning.
That sounds terrifyingly common for things like, say, amusement park rides or oil rigs, things that run constantly.
Absolutely. Designing against fatigue is paramount in those applications. Engineers need to know the material's endurance limit or fatigue limit. It's the stress level below which the material can supposedly withstand an infinite number of stress cycles without failing due to fatigue. This is determined experimentally by testing many specimens at different stress levels and counting how many cycles they survive. The results are plotted on an SN diagram, S for stress, N for number of cycles.
Okay.
For some materials, like steel, the SN curve often flattens out, indicating a true endurance limit exists. Below that stress, it should last forever, theoretically, maybe around 186 MPa for a typical steel. But for others, like aluminum alloys, the curve often keeps sloping downwards, even at very high cycle counts. They don't really have a true endurance limit.
So even low stresses might eventually cause failure if you cycle it enough times.
Potentially, yes. So for aluminum, engineers might define a fatigue strength at a specific very high number of cycles, like maybe 131 MPa at 500 million cycles. They design components to stay below those stress levels for their expected service life.
Wow. Okay, so pulling it all together, from one seemingly simple test, the tension test, and these related concepts, we get this incredibly rich picture. We understand how materials stretch and compress, how they yield and deform permanently, how they absorb energy, how they behave under shear, and even these hidden failure modes like creep and fatigue.
It really is foundational knowledge.
It really makes you appreciate the engineering hidden in plain sight. Like you said, a car bumper isn't just plastic, it's engineered for resilience. A bridge isn't just steel and concrete, it's designed considering yield strength, fatigue life, maybe even creep.
And connecting this back to the bigger picture, understanding these mechanical properties is absolutely not just academic. It's fundamental to safety and reliability. It's what allows engineers to choose the right material for the job and to design structures and components that are not just strong enough for the expected loads, but durable and safe, considering all the conditions they might face over their lifetimes: temperature, time, cyclic loading, everything.
So what does this mean for you, listening in? Well, maybe the next time you cross a bridge or fly in a plane or even just, I don't know, use a tool or open a cam, take a second to consider the unseen forces, the inherent properties at play. Think about how deeply engineered even the most common materials are to do their specific jobs safely and effectively. It definitely changes how you look at the world.
And maybe it raises a final question to ponder. Knowing just how much these properties can shift based on temperature, or how fast the load is applied, or the tiniest internal flaw, what kinds of unexpected material failures might be happening around us in everyday objects, things we usually take completely for granted, it makes you think about the hidden vulnerabilities in the manufactured world.